What's up guys, it's Simon Fiaz. Today's video is on question 10, AQA A-Level Chemistry, June 2020, paper 1, an actual A-Level paper, not AS. So we've got 10.1, 10.2, which is a very weird question. Never really seen a question like this before, where it's giving you a graph and it wants you to work out the entropy change, and then part 10.3, which is very simple. So 10.1, methanols form when carbon dioxide and hydrogen react. That's the equation. Table 5 contains enthalpy information and entropy data for these substances. Use the equation and data in table 5 to calculate the Gibbs free energy change in kilojoule per mole to power minus 1 for this reaction at 890 Kelvin. 6 marks. So first things first, anytime you get a question on Gibbs free energy change, 9 times out of 10 you're going to have to work out the entropy change. Unless they give it you in the question, which is unlikely, because if they did, it wouldn't be like a lot of marks. And every time I see these questions, it's usually more than 2 marks, 2 or more marks. So entropy change is equal to entropy of products minus the entropy of reactants. So entropy of products minus entropy of reactants, we're going to get entropy change equals products. What we're producing CH3OH 238, so it's going to be 238 plus H2O 189 minus entropy of reactants CO2 214 plus, well, if you think about it, because we've got 3 moles of H2, it's very cold in this room. Because we've got 3 moles of H2, it's going to be 3 times by H2, which in this case is going to be 131, and obviously put brackets around that. So entropy change is equal to, just put it in the calculator, and don't put all of it in the calculator because sometimes your calculator misinterprets it. Just do one step at a time. 427 minus, well, 3 times by 131 is 393. 214 plus the answer is minus 607. Therefore we get entropy change 427 minus 607 minus 180. Minus 180 joules K to power minus 1 mole to power minus 1. So now we've got the entropy change. That's not it. We need delta H. So delta H, enthalpy of formation, so products minus reactants. Products minus of reactants. Maybe let me turn it off. Actually, I'll keep it on. So now we get delta H as what's the products? Well, the products in this case is going to be minus 201 plus minus 242 minus reactants CO2 minus 394, and we should know, because this is just hydrogen, just a single element, the enthalpy of formation is going to be 0, and it tells us in the table is 0, so that's just going to be plus 3 times by 0, which is obviously 0, so we don't really care about that. So now if we work out delta H, minus 201 plus minus 242, so we get equals to minus 443 minus 394. Two minuses therefore becomes a positive, therefore we get delta H is equal to minus 443 plus 394 minus 49. And this is in kilojoules per mole to power minus 1. Now we can quite easily find out Gibbs free energy change, because that's what we're trying to find out. Don't really have a lot of space here. Well, we know delta H is equal to minus 49. Okay, don't do this in the exam obviously, but you can't. But I'm just going to remove all the working out and carry on from here. And delta H we got was what? Minus 49. So that's in joules. Entropy changes in joules. K to the power 1 minus 1 mole to the power minus 1. And delta H is going to be kilojoules per mole to the power minus 1. So Gibbs free energy change, the actual equation, delta G is equal to delta H minus T delta S. So delta G is equal to delta H, which is minus 49, minus temperature in Kelvin 890, so minus 890. That's pretty nice, because sometimes they'll give you the temperature in degrees Celsius. Students will be rushing the question, they'll use degrees when it needs to be in Kelvin, and then they'll get the answer wrong, so they'll lose at least a mark. So minus T delta S, which is minus 180 joules. And now here's where another thing comes in. We want the delta G Gibbs free energy change in kilojoules per mole to the power minus 1. This is in joules. So we need to divide it by 1000. So minus 180 times by 10 to the power minus 3, or divide by 1000, same thing. And now we get Gibbs free energy change. And instead of writing it here, I'm just going to write it here. Gibbs free energy change minus 49 minus 890 minus 180 times by 10 to the power minus 3. We get 111.2. 101.2. Moving on to 10.2. Use the values of the intercept of the gradient and so yeah, minus 49 minus 890 times by minus 180 divided by 1000, yeah, 111.2. Does it say to any significant figures? Nope, so it should be fine. So this wants us to work out the enthalpy change and the entropy change for this reaction using the gradient of the graph and the intercept. So this is a straight line, so it's going to be y equals mx plus c. You know, you learn this in GCSE maths, and you go through it again in A-level maths, because it's extremely important. Any straight line, we can use this equation generally. Y is equal to mx plus c. So let's write that down. Y equals mx plus c. Now if we look at y and x, well, we know in this case, this is obviously the x-axis. Basic knowledge of graphs, knowing which one's your x-axis, which one is your y-axis. So the y-axis is here. And now what we can do is we can basically construct an equation. So y So delta G, because that's the y-axis, delta G is equal to M, which we don't know, that's what we're trying to find. Yeah, we want to find the gradient. X, which is temperature, Kelvin, so T, so it's going to be MT, M, the gradient, T, plus C. And you can see how we've, it took a bit of understanding, and now we've easily converted this y equals mx plus c into an equation now where we can somehow build up and find the enthalpy change and entropy change. So we know that to find the y-intercept, the c value, that's when x is equal to 0. In this case, when t is equal to 0. So when t is equal to 0, what is delta G? Actually, well, if we compare it now, what's c equal to? Because we know c is going to be equal to delta h. Reason being, if we compare it to the actual equation, delta G is equal to delta h minus t delta s. Delta G's are perfectly fine. They're the same. The t delta s, so this tells me these two are the same. This tells me that delta s is a gradient. Well, it's going to be, because it's negative, it's going to be, so we know minus, when we know the gradient is equal to minus the entropy change. Negative version, well, doesn't necessarily mean negative. If the entropy change is negative, then it would be positive, so I can't really say that. And therefore C must be delta H. So C is equal to delta H. Okay, now if we want to find the intercept, the y-intercept, which is C, well, we know that's when t is equal to 0. And when t is equal to 0, delta delta G is equal to C, right? That's when t is equal to 0. When is t is equal to 0? T is equal to 0 here. And so what is delta G when t is equal to 0? Well, delta G is right here. And what is that point? That is 135, 140, what's it going up in? 5, 10, 15, 20, 25, 30, 35, 40, 45. That's 145. That I do not use Discord anymore. I don't know why it's sending me that. So that's 145. So we know delta G equals 145. But we also know delta G is equal to C. Therefore we know, and C is equal to delta H. Therefore delta H is equal to 145. So a lot of working out to find out. But we eventually get delta H is equal to 145. Now we want to find delta S. Well, we know delta S. Well, we know the gradient is equal to minus delta S. So if we just find the gradient, we can quite easily find delta S. Yeah, we can really easily find delta S. So the gradient, well, what is the equation for gradient? M equals y2 minus y1 over x2 minus x1. So the gradient is equal to, let's just use these 2 points here, and here. Makes more sense. So which one's y2, y1? This one is y2. This one is y1. Therefore this one is x2, y1, x2. This one x1, y1. So what is y2? Well, y2 is going to be, well, it's going to be 0. Yeah, y2 is 0. It's going to be 0 minus y1, which we know is 145, over x2, Well, x2 is, we're looking at this point here, 8, what's it going up in? Well, that's 9, that must be 900, so 8,200, 400, 600, 8,600, no, not 8,600, 860, 860 minus x1 value. Well, this x1 value is 0. Go here, that's when x is equal to 0. So this one is 0. So we get a gradient. Just need to practice this. And then you get a negative value. Let's keep as a fraction. Minus 29 over 172. But we know m is equal to minus delta s. So if we want to find delta s, that's going to be m divided by minus 1, which is minus m. And minus m is just going to be minus bracket our answer, which will give me 29 over 172. And now we need to, because you think about it, we've just found out delta s, right? But we found it out in, now we need to times by 1,000 because we found it out in kilojoules per mole to the power of minus 1. We want it in joules. So we times it by 1,000 and we get 168. That's obviously positive. And this is all, that's obviously positive. Okay, pretty hard question. That last trick, you need to time by 1,000, can definitely catch a lot of people off guard, including myself. Because if you think about it, we've worked out the enthalpy change in kilojoules per mole to the power of minus 1, and we've used the enthalpy change to work out the C value. No, we've used the enthalpy change to work out the gradient. 0 minus 145 over 860 minus 0. So this is going to be measured in kilojoules per mole to the power of minus 1. We don't want that, we're going to time by 1,000. And then say what figure 4 shows about the feasibility of the reaction. Well, let's remove, actually no. Remember when delta G is less than 0, feasible, reactions feasible. However, when delta G is greater than 0, not feasible. If you just learn those two key details, I can't really see an extreme, like when they ask you about feasibility, it's usually the same type of questions. So if you look at it, that's 860 obviously, or what is it, 820, 40, 60, I'm saying 860, it doesn't really matter. So if the temperature is above 860, well, delta G is negative, therefore delta G is feasible because it's a negative value. Negative is less than 0. However, when it's below 845, so here, well, that's delta G is greater than 0, therefore it's not feasible. So we need to write that down, type that down in this case. So when the temperature is above 845 Kelvin, reaction becomes feasible. However, when the temperature is below 845 Kelvin, reaction is not feasible. That's it for question 10.